Okay, guys, this is part two of the geologic time lecture. I'm going to start splitting some of these in half because if they get too big, I can't put them up on iTunes U, and then I have to re-record them. It takes extra hours, so I'm just going to play it safe because I already got burned once with plate tectonics. So what you want in front of you is in the Week 8 folder. It's called Simplified Geologic Timescale. Okay, so you want to have that. Now, if you look at this, this represents the history of layered Earth. And at the bottom is the beginning of layered Earth. And then at the very top, just at the top of Quaternary period, that's today. So this represents, about 4.6 to 4.8 billion years worth of geologic time. Now take a close look at it. Look at the numbers, okay? Mentally take those off. Now look at the strange names, and they're not strange to me, but I can see how they'd be strange to you. We already knew kind of the order of sequence of events because of the geologic principles. So the names represent kind of time periods, and only later on were the absolute dates added because we've only known about radiometric dating maybe for the last 60 years. So we were able to put things into, who came first, who came next type thing, and that's what these names represent. So we'll talk a little bit more about the names later on. All right, so the geologic timescale was first developed with relative dating. Only later did the numbers come about. All right, I'm going to simplify this a lot, you guys, and you're not going to have to, use this, or you're not going to have to create this from scratch, but you need to be able to use it as a tool. And basically there are 4 eons, even though this doesn't really show it. And what we're going to do is we're going to call everything in the Cryptozoic Precambrian, okay? And then in the Phanerozoic is the Phanerozoic. And Phanerozoic means visible life. Now, life evolved before the Phanerozoic. It's just we don't, have a whole lot of evidence of it. We do have evidence, but we don't have a lot of it, and we'll talk about why. Now, what I'd like you to do is get a black marker out and put a big black line, because I'm going to refer to the big black line, right at the 570 million year mark. And that would be, your line would go right between the Cambrian period and the Hadrianian period. Okay, and that's going to become important. And that's also the break between the Phanerozoic and the Precambrian time. And if you look at that, you're like, why Precambrian? Look at the very first period above the big black line. That's the Cambrian. Okay, so that's kind of what's important right now. Now, I have friends that got their PhD studying below the big black line. So, I don't want to say it's not significant. It's just not as well known. And in fact, what's kind of interesting is the time below the big black line is 85% of Earth's history. Okay, above the big black line is only 15%. And there's 2 reasons that we know so much about, the Earth above the big black line, and I'll tell you that later, okay? So below the big black line, important things happened. You remember one of those early in-class assignments that we talked about how Earth's atmosphere completely changed. That's important. And it completely changed with the advent of life, or the evolution of life, when life began. So the oldest known rocks are actually now at 4.3 billion years old. This is an old slide. The oldest known fossils are about 3.8 billion years old. And then what we have is about 2.5 billion years, we are going to start changing over to an oxygen atmosphere, an atmosphere with oxygen in it. So life evolved below the big black line. The atmosphere changed below the big black line. So, it was important what happened below the big black line. All right, so life evolved and the atmosphere changed. We got that. All right, so the Phanerozoic. Now you see, like I say, why is it 550 here, and why is it 570 on that paper, and why does it say 560 other places? That it's kind of hand grenades. As radiometric dating gets a little bit better, sometimes that number gets a little bit more narrowed down. But think about it, if you had $550 and if you had $570, it's pretty close. So I don't, you're not ever going to have to come up with that number. But if you see, a geologic time scale, the number will be on there, and then you could give it to me if I asked you for it. Remember, above the big black line only represents 15% of geologic time, or 15% of the Earth's existence. And the big black line, you guys, it's important. That represents where hard parts evolved. So hard parts, if I'm out digging, I work in fossil mammals, I typically find bones and teeth. Okay, but actually when I'm just out doing paleontology or messing around doing geology, actually most of the fossils I find are marine like clams and things like that. And so hard parts are things like shells, exoskeletons like a lobster has, teeth and bones. And life was alive below the big black line, but it was all soft-bodied. It wasn't until above the big black line that hard parts started to evolve. So obviously, if you have hard parts, you are much more likely to be preserved. So we have a lot more evidence of life above the big black line. Now I told you I'd tell you the second reason. The rocks are much less likely to be messed up above the big black line. You know, the older that continental material, even marine material is, the more likely it's been kind of trashed because it's been in a lot of fender benders. So the two reasons, hard parts and less likely to be messed up or metamorphosed. A lot of times metamorphism will remove all evidence of fossils. All right, now look at here and look at the word era. And there's three eras in the Phanerozoic: Paleozoic, Mesozoic, and Cenozoic. Paleo means old, Meso means middle, Ceno means recent, and Zoic means life. Now, you guys, the age of the dinosaurs was the Mesozoic. So we have organisms that lived that were older than there in the Paleozoic, and then right now we are in the Cenozoic. The Cenozoic is sometimes called the age of mammals. The Paleozoic is sometimes called the age of fish. And you can see that the eras are further divided into periods, and some of them have funny names. And then the periods are divided into epochs. If you look at the epochs, my specialty is Miocene epoch. Okay, so we'll talk a little bit about it, but not nearly enough. All right, let's talk about the Paleozoic. Remember, this is older than dinosaurs. And actually, a lot of these name changes that happen represent big extinction events, and especially between the Paleozoic and Mesozoic, that line that goes between the Permian and Triassic was a huge extinction event. The line between the Cretaceous and Tertiary, so Mesozoic and Cenozoic, is also a huge extinction event. So those names, you're looking at those names in the periods for the Paleozoic and going, what's Silurian, what's Ordovician? And little British school children are saying, what's Mississippian, what's Pennsylvanian? These are named after the type locales. And Ordovician and Silurian are named after native Celtic tribes in England, I believe. And obviously Mississippi and Pennsylvania are named after our states because the best examples of those ages of rocks are in Mississippi and Pennsylvania. Now, the base of the Cambrian, that's what basal means, the base of the Cambrian right there at the big black line. You know, why did hard parts evolve? Hard parts evolved because it was a time of very high sea level. It was actually a pretty warm earth. And you guys think about all the yummy seafood we like to eat. And at this point, all the organisms were aquatic. You know, it all comes from the continental shelves. And during times of high sea level, you know, there's a ton of continental shelf. And so all this new real estate opened and animals started breeding like crazy, and what are they called? Mutations. Mutations came about, and not all mutations are bad. Think about it. You're a slug, and you have children, and your children have shells, and they're like snails. You know, you're more likely to get slurped up and eaten by something because you're easier on their teeth. You know, maybe if you have a shell, you can hide inside that shell, or it's hard, and so something can't eat you. And so you're going to live to reproduce. So this is how it happens. So not all mutations are bad. And so actually hard parts like shells evolved, you know, in many different lines. Okay. It's also known, the Paleozoic is also known as the age of trilobites, and trilobites were cockroaches of the sea. Luckily they went extinct, otherwise I would not want to go in the ocean. Okay, here are some different trilobites, and these are very common fossils to find. If you guys go on our Death Valley field trip, we might stop at a quarry where we pay a few bucks, we break open some rocks, and we find beautiful trilobites like this. And, you know, these are the type of fossils that maybe you could find in Siberia or in England, and you could actually match the ages of those rock groups. All right, now the Carboniferous has been split into the Mississippian and Pennsylvanian. And during the time of Pangea, remember from the plate tectonics lecture, North America was over the equator. And so this was a time where we had a lot of these coal swamps. And now, you know, they were basically tropical rainforests, but the the plants that live in tropical rainforests today had not evolved yet. These were kind of like your Christmas trees. Christmas trees are gymnosperms, fir and pine and sequoia and stuff. And they died, the leaves fell or the needles fell or the branches fell, and they got in that mud, got cut off from oxygen and produced huge, huge deposits of coal. The Pennsylvanian is very famous for its coal deposits, and that's because North America was right on the equator at that point. All right, at the end of the Paleozoic was actually the biggest extinction event ever. It's called the Permo-Triassic extinction event. Something like 90% of all organisms went extinct. And, we don't have a smoking gun for that one, but we do believe that it had to do with some incredible volcanism that happened up in Siberia. So this is kind of exciting because this is, a paper was just written about this in the last couple of months. All right, when all those organisms died, and then new organisms evolved, and there was all these open spaces, dinosaurs evolved in the Triassic, and changed a lot over time, and so the Mesozoic is called the Age of Dinosaurs. Now, I heard a kid one time say, "Oh, dinosaurs are losers. They went extinct," and you want to grab that kid and say, "No, dinosaurs are winners. They were around for 180 million years. They were very successful." And you know what? They didn't ruin their environment like we're doing. They had an external source that they couldn't control that ruined their environment. So they were very successful. You guys, humans have only been around like 100,000 years. If we're around 200 million years, maybe we could say they're losers. I don't think so. So the end of the Mesozoic is marked by a giant extinction event, the dinosaurs and some other species. And they actually have a smoking gun. A father-son team from Berkeley won Nobel Prizes. All around the Earth, they found a rich iridium layer right at the time when the dinosaurs went extinct. And iridium is not very common on Earth, but is very common in large space objects that hit Earth. And so they do believe that Earth was hit by a large space object, probably an asteroid, and it basically made the environment such that dinosaurs couldn't survive. Remember, they're reptiles, probably, nuclear winter or something. And they found, using remote sensing, the big hole in the bottom of the Gulf of Mexico. Now, you guys, mammals were already alive, but we were really insignificant. Dinosaurs were the dominant life force. We were kind of like pocket gophers, and it's what saved us. Mammals lived underground and were able to survive and maybe hibernate or had food stores or something like that, but they made it through. And when they came out, after the environment cleaned up a little bit, there was all these open spaces and all this environment for them to go crazy. And they did that. They bred like crazy. And we call it speciating or radiating. Now, remember, at this time, the continents were more apart. So we had some very specialized organisms on the different continents. So this is actually, the Cenozoic is referred to as the age of mammals, but it's also referred to as the age of flowering plants. Now, you guys, if you go out on a spring day and maybe you curse the flowering plants because of your allergies, but you see all the beautiful flowering plants. Right now, it's already happening. And, none of those organisms lived before the Cretaceous. They evolved. And so, they also made it through the KT boundary, or the end of the Mesozoic extinction event, and then just went crazy. The gymnosperms actually made it through too, and you know that because of Christmas trees. The earliest hominid fossil is dated at about 6 million years, the Miocene. But you guys remember, these guys, Lucy, they're older than Lucy, Artie, Lucy, and there's even an older one. They don't look a whole lot like us. Homo sapiens, they don't think have been around for more than 100,000 years. All right, the Pleistocene. Now, I would, of course, love to talk about the Miocene because it was very exciting, but let's talk about the Ice Age because I think all of you guys are pretty comfortable with the Pleistocene epoch. And it only ended, 10 to 12,000 years ago. And in our area, there's actually in Placer County, there was glacial ice up near the Rainbow Lodge. There's probably about a mile of ice on there, and the North American continent was covered very deeply in ice that came down to, continental ice, came down to about Kansas and Nebraska and things like that. So they probably, North America looked a lot like maybe Greenland and Antarctica. And obviously Greenland and Antarctica still have ice on them. So Pleistocene is kind of known as the megafauna. You had saber-toothed tigers, woolly mammoths, mastodons, things like that. And we actually have a lot of Pleistocene fossils that come out of the area near Arco Arena. When they were making Arco Arena, they dug out a lot, and they're actually in our museum. You should check them out. All right, so the geologic timescale, you guys don't have to memorize it. If you go on in geology, you will have to know it forwards and backwards, but it's not just memorization. You'll know it. It'll make sense to you. But you will be using this as a tool. And in fact, one of your in-class assignments, the fossil assemblage one, check out that handout, that geologic timescale. It's the one with has the pictures of the organisms on it. I could ask you questions right off of that, and look at that. You could actually answer them as long as you know how to use the tool. All right, I just want to say something about radiometric dating. Remember, radioactivity was discovered around 1900, and then it took us a little while to learn how to use it as a clock. But not all rocks are dateable. Don't go to the beach, pick up some sand grains, say, oh, I'm going to date this beach, because what you'll be dating in Northern California is the age of the Sierra Nevada granite, where the sand grains or quartz grains came from. So you don't date sedimentary rocks, but a lot of times, what you can date, igneous rocks. Igneous rocks are the best. I know when igneous rocks are born. They're born when they crystallize, when they go from magma or lava to a solid rock. And so let me show you an example, you guys. This is actually a place where we sometimes go when we go dig fossils in the summer, and the Morrison Formation is a very famous dinosaur bearing formation. Now look at it, there's a volcanic ash bed right above it. What can I say about the Morrison Formation? It has to be older than 160 million years, because that 160 million year old ash sits above it. What can I say about the Dakota sandstone? It must be younger than 160 million years, because I find it sitting on top. Now we can also look at that igneous dike that's 66 million years, so I know the Dakota sandstone has to be between 66 and 160 million years. You can't, I can narrow it down using fossils and stuff, but right here, that's all you can say. The Manco Shale must be older than 66 million years old. And so, we usually can bracket it pretty well, and then we can use fossils to figure it out a little bit more carefully.